Hello, this is the last session in December. However, I will have at least, and probably at most as well, 3 sessions in January. I'm trying to schedule them for, I believe, the 22nd, the 23rd, and the 24th, which are just before the final, which is on the 26th. And I will do the finals on Saturday morning, right? So I will do a complete review of the post-midterm material, and then have enough time for plenty of questions and answers. Okay, so here's the deal for today. I'm going to finish, I'm afraid, at 9:45. That's just what it's going to be. So this will be a little bit late. You don't have to stay. If no one stays, I'll just talk to the video, and you can all watch it later. That's cool. But I need to cover almost the rest of the course. So there you go. Last week, I kind of fumbled around, and I'm sorry. I'm equally tired this week, but maybe better prepared. So, what I'd like to talk about can be encapsulated in 2 things. Line integrals, surface integrals. That's what I'm going to cover, okay? So, let's just start off with line integrals. When I do surface integrals, we'll see a relation with line integrals right at the end. But, I talked last week at considerable length, and as I said, with a little bit of muddle, about line integrals. So here is the basic synopsis. The first thing I'd like to remind you is the idea of general line integrals, i.e. 2D or 3D. Then we've got this notion of conservative vector fields and their relation to line integrals. And finally, I'm going to look at line integrals in a plane, and that's going to lead us into Green's theorem. Okay, so that's the agenda for the first half. Okay, so last time we looked at a general line integral, and we saw there are a few different ways, but the most common type of line integral we saw was f dot dr. So this is step 1. F dot dr, where f is a vector field in space, or possibly in the plane, but f is a vector field, otherwise known as a function that takes every point in space and attaches a vector to it, and does so in a nice smooth way, so that points near each other have vectors near each other. So I think of it as a bunch of vectors that are sort of aligned when you're close together, and I can't draw them all because they have different lengths and different directions. There's one everywhere, but I can only draw a small sample of them. And that's 2-dimensional, of course 3-dimensional would be there. So think of it as a sort of flow type of object. F dot dr, okay, so we have this curve going through C, and R is x, y, z. It's a vector, it's a point on the curve. So for different points on the curve, you have dr as the tangent vector. We're basically taking the dot product at every point on the curve of our flow with the direction we're going on the curve, and we're adding them up, multiplied by the length of the curve. So it's a sort of complicated thing, but it actually was not so bad to calculate in practice. All we did was find a parameterization, so we found a parameter t, and then r was a function of t, because you see x and y and z are functions of t. And so dr was just equal to dx dt, dy dt, dz dt, dt. Let's move that c over here. So it was exactly what you thought it should be. And then f you just wrote in terms of t, and you just took the dot product and did a regular integral. So that's sort of a summary of what we did for a lot of last week. Now, as I said, I spent quite a bit of time on that. So what I want to do now is go back to what I was doing at the very end and look at a conservative vector field. Okay, so just by way of review, here is the deal. We have 2 points, so A and B, and you have some curve joining them. And I'm going to presume that we have a vector field defined on a very nice region of space. This could be in space or in the plane. So when I say nice, I mean it should be connected. I don't want it to have separate parts. That's no good. And also simply connected, which means I don't want it to have like a hole where that's missing. It kind of has to just be a nice solid blob. Okay, so without going into the topology of the situation, let's just say it's a nice blob. It doesn't have to have a nice boundary. It can be quite a misshapen blob, but it's in one piece with no holes. All right, now I'm going to form an integral like this. So I have a vector field defined on this blob, and I have these 2 points, and I take a nice curve C. Now when I use the word nice, it means essentially C is smooth, except that it can have a finite number of corners. So I'm allowed to do something like this, because there's just a few bad points. That's okay. I can just do a bunch of different integrals and add them up. If I have infinitely many sharp points, that could be a problem. Anyway, so let's just assume we have finitely many. Here are 2 different curves getting from A to B. You get 2 different integrals. I should have put the C here. Okay, so you have 2 different integrals. And you probably will get 2 different values, depending on the curve. But there are some special vector fields F where this quantity, f dot dr, is the same for any curve A joining, any curve C joining the points A to B, from A to B. C has to have direction. You get the negative answer if you go backwards. So basically then you want this, if this is the same, then F is conservative. And this is true for any pair. This has to be true for any pair of points, A and B as well. So if basically you have path independence of the line integral, that's what this is called in a nutshell. Now, this actually turns out to be the same as saying, alternatively, it's the same as saying that the integral of f dot dr is equal to 0 for any closed curve C. Closed in this case means a loop. Okay, so why is that true? Why is that an alternative condition for conservative? That this is equivalent to this pathwise independence. Well, it's not so bad. I mean, if you get the same integral going from here as going along here, so you get some value for the integral there, you get some value going there. Well, what if you instead go backwards here? Well, you get the negative of the value, because f is the same, but dr points the other way. So dr is the negative vector of what it used to be. So that means that if you go around this whole loop, then you're doing whatever this was, plus the negative of this, which is 0. So you reverse what you did. Since it's path independent, you may as well have gone there and back again. It doesn't matter that you're going around a loop. So actually, that condition implies this condition. But this one implies this, because if you want to see that 2 paths are the same, well, you know the loop is 0, so you just bust it up into this piece plus this piece. They add to 0, so this piece equals this piece. So it's just a nice observation, really nothing too deep in it. Although the topology can get quite tricky if you really try to get into it. So this is what we mean by conservative. And now last time we saw that if you have a conservative vector field, there is a potential f, which is a scalar function. This is a vector function or a vector field. F is a scalar function such that f is equal to grad f. Capital F, the vector field, is grad f. Remember, this is the vector field df dx, df dy, df dz in 3 dimensions. In 2 dimensions, you don't have the last coordinate. So there's a sort of antiderivative, but it's a complicated antiderivative. You should think of this potential little f as an antiderivative for capital F.
Because f is a scalar, how are you taking derivatives of it according to x, y, and z?
Well, when I say it's a scalar function. Maybe I should have written x, y, z. As opposed to capital F of x, y, z, which gives you a vector for every point. Little f gives you a scalar for every point. You can sometimes call it a scalar field because there's a different number at every point in space. But a vector field is a different vector at every point in space. Okay, so this vector field is the gradient of a scalar field, which you can see from the formula. Yes, you do get a vector. And we observed this last time. That's a very important vector field is the gradient of a scalar field. All right, so if that's true, then there is this potential. And you have a beautiful formula that if you want to compute f dot dr over any line integral, you don't need to find a parameterization. You don't need to do all that stuff. All you have to do is you find the potential little f, and you compute f of b minus f of a, where a and b are the start and end point, respectively. So start is A and B is the end point of C. This says respectively, but C goes from A to B. So you actually only need to know the beginning of C and the end of C. And then you just plug it into this potential. Okay, so this we saw last time, or at least I said it at the end.
How do you find the gradient?
Well, I gave an example. I'm going to revisit that example. But first, I would like to show you an important thing to do first. I have said if f is conservative, it is a very extraordinary thing for f to be conservative. Your arbitrary general vector field that you stumble across is not conservative. It is a very special thing to be conservative. Okay, so before you go to the trouble of trying to find this potential, it would be nice to have a condition to check that f is conservative. Without even, like, how do you even know? And the best way to state the condition, although the textbook doesn't quite do it this way, is to use something called the curl of f. Now, we're going to need curl very soon when we do Stokes' theorem. And even when you do Green's theorem, you really should state it using curl, and the textbook does. So I have no idea why they don't just state it one section earlier. I'm sure they have an educational reason. To hell with them, I'm going to do it. Okay, so here goes. We have a vector field f. I'm going to define the curl of f, which is also written as the del symbol cross f. And here f's going to be three-dimensional. Cross products only work in 3 dimensions. So I'm going to take del cross f. And this is going to be a new vector field which has the following formula. It's exactly what you hope. In a symbolic sort of way. It's a cross product of this cross f. Well, let's assume that f actually is the vector field, say, m, n, p. And that is another way of writing mi plus n, j plus p, k. And these are functions. These are scalar functions who are the components of the vector f. So if f has this field, this form, then you're going to take this cross f. Well, the bottom row is just going to be the coordinates of f. But what's the middle row? Well, the middle row are not actually going to be numbers. They're going to be derivative operators. But they're the derivative operators that appear in the del itself. So we've seen this is a different usage from this del f, although it's sort of compatible. I mean, if you think of the del symbol as meaning this vector, ddx, ddy, ddz, and you apply it to a little f, just a scalar function, you get df dx, df dy, df dz. Well, now we're going to apply it to f, and you get this. And this is now going to be some other vector field, another vector field. All right, well, what's it good for? It's good for a number of things, but the first thing that it's going to be good for is to check whether a vector field is conservative. So f is conservative. A way to check. You need this curl to be 0, and that's a vector field 0. That's the condition. That's the easiest way to remember it. The textbook has a much more complicated way of describing it, but essentially what they're saying is that the curl is 0. So where am I? All right. So the example that I looked at last week, which I will redo because I kind of rushed it and I wasn't able to do this part of it, it said, consider a vector field that looks like this. F is equal to x squared plus y I plus y squared plus x j plus e to the z k. And it's asked you to show that the work done by this field is the same over any path from A, which was 3, 0, 1, to B, which is 2, 1, 1. Okay, so as I said, I did do this example before, but I really didn't have enough time to explain it, so I kind of want to do it again. Apologies if you already understood it well last time. Okay, so you want to show that the work integral is the same. Now remember, a work integral or a flow integral, it's the same thing. We're basically trying to show, we have to interpret that statement, the work integral is the same over any path, as meaning that f dot dr is the same for any c joining A to B. That's what we want to show, i.e. f is conservative. That's what we want to show. i.e. we need to show, according to what I've just said, that the curl is 0. So that's going to be our approach. I haven't done anything fancy. All I've done is interpret the question. Right? I read out the question to you, but anyway. I didn't write it up, but that's what it asked you to show. All right, so let's compute the curl of f. Not so bad. We know how to take a cross product. We just need to know what this curl operator is. Well, it's just the del operator cross f. So what do we stick here? We stick the coordinates of f. X squared plus y squared plus x, and e to the z. We need to compute that. So how many I have we got? We've got d dy of e to the z. Now remember, these are partial derivatives, so they're independent. d dy of e to the z is 0. d dz of y squared plus x is 0. No problem there. So for j, we need to take the negative of d dx of e to the z. Well, that's 0. And we need to add d dz of x squared plus y. Well, that's 0. Gee, this is easy. Well, the k is a little more complicated. K, we need d dx of y squared plus x. Well, that's just 1. And then we need minus d dy of x squared plus y. And wouldn't you believe, 1 minus 1 is 0. So this is the 0 vector. It's 0i plus 0j plus 0k. I mean, it's not wrong to write 0 without the underline, or without an arrow on the top if you prefer, but it's kind of classier to realize that that's a vector. So since the curl is 0, f is conservative. And we have proved, without even finding the potential function, that there is a potential function. But as it turns out, part B is to compute an integral of, in fact, compute this integral here. So now let's do it confident in the knowledge that we can. I'm going to need a little bit more room. So this is the part that I did last time. I actually had skipped part A. But now I'm going to show you the solution once more and take a little more time over it. So we are looking to solve grad f equals capital F. And just for reference, capital F, I just let me write that again. I write it in component notation. Is it y squared plus x? No, x squared plus y y squared plus x, comma, e to the z. That's what we're trying to find. We need to find little f, such that that's true. All right, well, this is equal to df dx, df dy, df dz. So we have to just equate coefficients. In other words, we're trying to solve these three equations. df dx equals x squared plus y, df dy equals y squared plus x, df dz equals e to the z. Okay, so I've just copied the components of this and the components of this and set them being equal. So in order to do this, I have to integrate, but I have to do it in a clever way. Let's just integrate this with respect to x. And we will see that f is equal to x cubed over 3 plus xy plus constant. Now, what's constant? Constant with respect to x, but it could still depend on y and z. So I'll call it c1 of y of z. It's a constant, but it's not really a constant. It's a function. The point is it does not depend on x. Now I repeat this, except now for the second one, I integrate with respect to y. And I will find that df dy is equal to y cubed over 3 plus xy plus some other constant. And now this constant doesn't depend on y, but it does depend on x and z. And finally, integrate the last one with respect to dz, and you'll get f equals e to the z plus some other constant, this time depending on x and y. And what you have to do is take these three expressions for f and amalgamate them, make them all true. And so it's not hard to do. If we try to amalgamate these, you might then have an x cubed over 3 plus an xy from the first piece. That's from up here. The second piece, we already have the xy. We need a y cubed over 3. And the second and the last piece, you need an e to the z. And finally, there will be some constant, which is a number. Now we write this down, and let's just do a reality check to make sure it stands up. It needs to basically satisfy all three of these. Now, you don't have to do this in principle, but you might have to write down what these are. According to the first equation, which is way up there, C1 needs to only depend on y plus y and z. That means all the bits which are not x cubed over 3 plus xy have to have no x stuff in them. So if you come back down over here, this is consistent with C1y equals y cubed over 3 plus e to the z plus c. Yes, that satisfies now the first equation. And of course the second equation would be satisfied with C2 of xz being x cubed over 3 plus e to the z plus c. And finally the third equation, which only involves the constant being an x and y, will work if it's all these xy things. And if you look at these three equations and you plug them into those three equations, you will find that in each case you get the actual f. And it's a sort of minor miracle that they're all consistent. Well, the reason they're consistent is because we checked that the curl was 0. Otherwise it won't work. Question?
Or when you had the C1, 2, 3.
Yeah, C1, 2.
Is that C the same for the whole f?
Well, they're three different functions, C1 of x, C2, and C3.
Yeah, but the plus C at the end.
Oh yeah, the plus C at the end is the same. Yeah,
Okay.
it has to be. I mean, actually, you can omit the C if it says find a potential function. But there's always some ambiguity about one constant in the whole thing, because you're doing a derivative of each of the terms, right? But you need it's just one function that's needs one constant. So this is sort of optional. You certainly don't need it to find the integral, because just like you don't need it to find a definite integral, you never put the plus c. So to find a potential function, you don't need the plus c. To find all the potential functions, you need to allow the ambiguity. But it is the same c for each of the three. Anyway, we can now complete the question. What we're trying to find is the integral of f dot dr from over C, and what was it? 301, C joins 301, goes all the way up to 211. So this is just equal to little f of 301 minus little f of 211. So we're thinking, this looks like an antiderivative. Little f looks like an antiderivative. And it is. After all, the derivative of this, little f, is capital F. But when I say derivative, it's of course grad f. So it's a sort of weird derivative. Anyway, we have our f up here, so we simply substitute. It's 3 cubed over 3 plus 0 cubed over 3 plus e to the 1. And we don't need the plus c. And then we have to substitute in 211. And you get 2 cubed over 3 plus 2 times 1 plus 1 cubed over 3 plus e to the 1. And you see, if you did put a plus c, then you'd also have a plus c there. It has to be the same c. And they'll just cancel out because of the minus sign. So you don't need the plus c for that. Anyway, if we compute this, you get 27 over 3 is 9 plus e. 2 cubed over 3 is actually 8 plus 8 thirds plus 1 third is 9 thirds, which is 3. And then we have to subtract another 2 and another e. So it works out to be 4. And that's true no matter what curve you integrate over. Okay, so that example's pretty canonical. It's pretty canonical. The only other sort of example that I've seen gives you a vector field f, where instead of looking like this, it has, you know, there's another light there, isn't there? Man, sorry. This could have made, is that it? That's something. Ha, there we go. All right. Understanding dawns with the light. All right, so the point is, the only other type of example that you commonly see is where you have some a or b that's unknown in front of some of this stuff. And they will say, for which values of a and b is the field conservative? And then you have to compute the curl, and you have to solve the equation for a, b, c that make it 0. But it's not very different. All right, so that's what I want to say about conservative vector fields. Are there any questions before I move on? If so, please even start as I erase. No questions? Just a bit of laughing. All right. Question. Please.
Is the work done in the closed loop 0?
Yep. The question is, if you have a closed loop and f is conservative, is the work 0? Thinking of f as a force field, of course. I mean, for it to make it sense as the physical term work, it needs to be a force field rather than a flow velocity field. But the point being that if they ask this question, for C being any loop that starts and ends at 301, say, then you would actually plug in 301 to both of these and you get 0. So that's another way of seeing that the closed loop is 0. Another question over here.
I understand how to do it, and I was trying to read the book and follow the theory, kind of, but I didn't quite understand, like, why is it that gradient field, or gradients are conservative?
Why is the gradient field what, sir?
Why is that this is true? Like, why are only gradients conservative and nothing else? Like, I understand that it all needs to be 0, but...
Well, right. This might make more sense after we do Stokes' theory. Okay? And that's really where this is coming from, as it turns out. So, yeah, it's a good question. Why is it true? But I can't really tell you yet. But if we have time, we will see why it's true. Another question.
I just wonder, for that integral, shouldn't b be integrated? Shouldn't it be equal to...
Oh, hell, I got it the wrong way around, didn't I? Ah, thank you, thank you, thank you. Okay, come back over here. This is the first of the mistakes. It goes from f of a it goes from A to B. This should have been f of B minus f of A, so I got this exactly the wrong way around. So this should have been 2, 1, 1. Did I do this wrong last week as well? Anyone remember? So basically, this should come out to be minus 4. Not 4. I got it the wrong way around. So, humble pie, number 1. But keep the mistakes coming as you notice them. Let's see if this is consistent with what I wrote for myself. Well, on my notes I wrote minus 4. So, there you go. Last week I suspect I wrote minus 4 as well. So, strike 1. All right, any questions about that, how I screwed that up? Does everyone understand that it should have been f of the final point minus the initial point, not the other way around? Okay, another question.
When they're asking us to do something like this, or when they're asking us to find work over a vector field, will they generally tell us if we should be attempting to do it using a potential function, or?
So the question is, in terms of practicalities, they say find the work over a vector field. The question is, do you try to see if it's conservative or not? In this problem, it was very clear that we had to do it because part A said show that it's the same. Right. If not, then you have a choice of 2 methods for finding a work integral or a line integral like this. You can either A, take a chance, and if it's 0, find the potential and have a much easier time. Or B, by the way, if it's not 0, you have to go to B, which is do it with a parameterization, as we did. So it's a gamble as to whether you try for the potential function version. Okay? If you are right, it will save you a lot of time. If you are wrong, you will have wasted time by computing a curl. But the curl doesn't take that long to compute, so it may not be a bad strategy. I would advise do a bunch of past finals, and you will get a sense for how many of the ones which don't tell you to check whether it's conservative are actually conservative. It's not a very hard thing to compute a curl. It's just it's a cross product with a bunch of derivatives. But it will still take 45 seconds or so, or a minute, or it depends how complicated the function is. All right. Moving on to Green's theorem. All right, so I want to look at line integrals just in the plane. So line integrals in the plane. Okay, so I'm going to distinguish between 2 types of line integrals. So I actually even want to consider only a closed loop C. So let's say we have a closed loop C that's simple. I'm not even going to allow it to cross itself, although maybe we could. Let's just make life simple for ourselves and take a simple curve. So that's C, and I'm going to assume in general that it's counterclockwise is the way we're going around this. I'm sorry, it's in the plane. We're working in the plane. All right, so we have this closed curve and we're proceeding once around counterclockwise. That's what the definition of C is. And we're going to look at this line integral here, f dot dr. And I now am putting this symbol around to indicate that it's a closed curve and we're going around once counterclockwise. All right, so this is exactly the same as what it meant before. It's exactly the same, but there is a nice way of writing it which I kind of got bogged down. Here, f is equal to m comma n. We don't have a third component because we're in a plane. There's only 2 components. And what I want to do is, if I write it out, this is another way of writing this, which is good for computation, and this is where I really got screwed up last time, not on that particular formula, but I have m dx plus n dy. Now, that's just an abbreviation, in a sense, for the fact that r is equal to xy, so dr ought to be equal to dx dy. Okay, so if I took the dot product of fdr and fdr, you get m dx plus n dy, which is exactly what's written there.
Why does r equal xy?
R is just the position vector. It equaled xy over here as well. Well, I've erased it, but r is the position of where you are. Before it was xyz. If you look back at the beginning of your notes, you'll see r is xyz. This is just the generic notation for where you are. So when we've been writing dr, we mean the change in position of where you are. Okay? Okay, so dr is the change in position, and you get this. Now, it still doesn't tell you how to compute it, And in general, the way to compute it is, again, to let x be x of t and y of t. And you just replace m, and you compute dx in terms of dt and dy in terms of dt, and it reduces to a regular integral. So there's nothing new there. Now, in terms of interpretation of what this integral means, take a little point. F is a vector field. There's F, say. Okay, dr points along, it's a little bit along the direction of C. And the dot product tells you essentially how much of this vector is pointing in this direction. So the dot product is essentially equal to, it is equal to, the projection of this vector onto here. It's the product of those two. So what we have then is we're only interested in the part of the flow of, so imagine there's a bunch of gas flowing up through around here. And the F tells you the direction of the flow. So it might change. I kind of want to know what's the net flow of the gas around the loop. So maybe instead of thinking of it as a gas, think of it as a bunch of like marbles rolling along. But what I want is have a little track going along around here. Now the problem is that now think of it instead of marbles as the wind blowing the marbles in this direction. So with left to its own devices, the marbles are going to go. Okay, so now make a little track. So take a marble and constrain it so that it has to go along the track, but it still experiences the wind. Well, the wind's blowing this way. It wants to go this way, but it's stuck in the track. So it's only the bit of the wind blowing along the direction of the track that actually moves the marble. The rest of it is sort of, it can't move in this direction. So the marble moves around. And if you imagine a whole lot of little marbles around everywhere, see how much they want to move around counterclockwise. Some of them might want to move the other way. So there's this sort of push and pull. And we want to measure the average flow of the marbles going around. That's a physical interpretation of what that integral means.
How would they ever get down the other side?
Well, maybe they won't. I mean, you know, here in this picture, this one might not really move. Like if it's going across, it won't move at all. And f dot dr would actually be 0 at that point. Yeah. Okay? So what I want to do is I want to look at each marble. Each marble has a push either forwards or backwards around the circle or around the loop, or not at all. Maybe it has a 0 push. And I want to take the average push around. So, you know, the average will, in the end, you know, they'll jostle each other and it'll give you an idea of the average flow around the thing. Okay? You know, some of them are fighting against, but the overall direction might be this way, in which case you'll see it'll gradually push each other around. So that's what I mean by the flow. Okay, so it's measuring the circulation around the loop. So this is also called circulation. Okay? Question?
So if f was a conservative vector field over this, you would get a value of 0 for the total?
If f is a conservative vector field, you get a value of 0. That's right, because the integral f is 0.
A similar way to check for conservative fields?
Oh, absolutely. You're going to take the curl, and the curl only works in 3 dimensions, so we're going to have a comma 0. But again, Green's theorem will throw some new light on this, and I will show you very, very shortly about this. All right. Now, given this, I would like to state a form of Green's theorem that's actually the second one stated. In fact, I will answer your question right now by showing one form of Green's theorem. And this is actually version 2 in the textbook, but whatever, they're the same theorem. Here's what it says.
We're still in the plane?
We're always in the plane. Green's theorem is in the plane. Okay. In fact, it's sometimes called Green's theorem in the plane. Okay, so until I say otherwise, we're in the plane. Okay. Although I kind of need a third dimension to define this. But look, okay. Well, no, actually, I'm going to need to say it. My next thing I'm going to say is imagine that this is mn0. Okay, imagine this is mn0. Okay, it's in the plane. We've got to allow ourselves a mythical third dimension, but luckily everything is 0 in the third dimension. All right? So what is the curl? What is the curl? The curl would be I, J, K, dx, dy, ddz, m, n, 0. they're functions of x and y alone. Stokes' theorem is what we need to push Green's theorem into 3 dimensions, but that's later. For the moment, we're in the plane. Okay, if we do this, we will see that the I component is d dy of 0, which is nothing, minus d dz of n, which is nothing. Why? Because n doesn't depend on z. And you'll find the same thing with j. d dx of 0 is 0, d dz of m is 0. This is basically never going to come into play. But the k thing is important. K, we have dn dx minus dm dy. Okay, so in terms of the curl of f, it's actually in the k coordinate, so we may as well think of it as just being a scalar. Although it is a vector, we may as well just think of it as being dn dx minus dm dy. So here is what Green's theorem, version 2, and as I said, I'll come back and do version 1. Here's what it says. The line integral, now behold, this is a really cool theorem, actually. The line integral that we've just looked at in the plane is equal to the k component of what we've just got, dn dx minus dm dy, the double integral dx dy over a region R. And what is R? R is the interior of C. Blech. What on earth does this mean? Okay, what it says is you can change a line integral around the boundary into a double integral of the area sort of some other thing. Now, in order to make more sense of this, this is the form where it's really easy to compute with. This is a really good thing to remember because it makes the computations very straightforward. But you can also do computations with the other form, and the other form is what's really going on. Here is the truth of what this is saying. No, this is still version 2. Version 1 has normals instead, f.dn. So this is the other way of writing version 1, but without version 2 rather, but without using m and n. The integral around a loop is the same as the curl of f, but we need to dot that with k to get the k coordinate and make sense of that. dA. Now, in order to convince you, once again, that this is exactly the same thing as what I just wrote, we've already seen that that equals this, f.dr. And as for this, the curl of f, we just computed this. The k coordinate is exactly this quantity here. And when you dot this vector with k, if you just whack a dot k, k dot k is 1. Why is k dot k 1? It's just the absolute value of k squared, the length of k squared, which is 1, because k is the unit vector in the vertical direction. I dot I is also 1. J dot j is 1. K dot k is 1. They're unit vectors. N dot n is 1 if n is a unit vector. Okay? So this is true for any unit vector k. Any unit vector. Alright, so when I dot the k, this is just a formalism. I mean, you could more or less write that without the dot k, and then you would only be slightly wrong. You would end up with a vector instead of a number. But the vector would be 0 in the I and j components, and you know, it would be pretty clear what you meant. Anyway, okay, this is a very strange statement. Let me try to explain why it's true or what it means. The flow induced by this wind of marbles just around here. Well, it turns out that the curl of f says that if you're here and you place a little paddle wheel And so now I'm imagining the marbles as being locally around here. I kind of want to know if I have marbles very close to here and I put a pole there, the marbles will sort of surge around the pole. Right? Some of them will go like this, some of them go like this. Maybe there's more of a movement that is in a counterclockwise direction than in a clockwise direction. Another way of thinking of it is do exactly the same thing that I did before. Here's a point, take a tiny little track around that point and put a marble on that, put marbles around there and see how many of them want to go this way and how strongly and how many of them want to go that way. Maybe there's an equilibrium and none of them really want to move at all. But then the curl would be 0. So the curl measures the strength of the move around counterclockwise. That's essentially what it measures. Why is not obvious from these things. Physicists were very clever to boil down these concepts to smaller, to actual formulas. But basically then, it's true for a very small loop around. The book also talks about a paddle wheel in a gas. I mean, you stick a paddle, this is the flow of a gas. You stick a paddle wheel there and you see whether it turns that way or not at all. So marbles, paddle wheel, that's the same sort of thing. Now, according to this formula, what you have to do is add up the curls, as in these sort of mini circulations, at every point inside. That's the right-hand side there. Add up the curl. They all point in the same direction, either this way or this way. So if it's counterclockwise like this, that gives me a curl that points that way. If it's clockwise, the curl points into the board. And if it's 0, then it's 0. But we only have a k component, which is in or out of the board. Now here's the beautiful thing. I'm going to add them all up. Okay, you get the idea. It's actually adding it up, infinitely small circles everywhere. But the beautiful thing is that somehow there's a whole lot of cancellation. For example, if the marbles want to go this way here, then on this touching circle, they also want to go this way. So for this circle, the contribution of the marble is positive because it is going counterclockwise. For this circle that's touching it, it's actually going the other way. So it counts negative, and there's a certain cancellation of just that little bit. And what this is saying is if you add up all of those circulations with all the cancellations, they sort of everything cancels except for the bits at the boundary. And what you're left with is just the overall circulation around there. So there's sort of...
It's so ridiculous.
Yeah, but it has its... It is ridiculous.
It doesn't really tell you that at all, so you're just like, oh, let's just plug in all these formulas they give me.
Well, it mentions paddle wheels, and you know, if you're using the paddle wheels, the textbook, you kind of want to think of interlocking paddle wheels, right? You put the two together, and if they're both turning in the same direction, then they sort of will hit each other and cancel each other out. But at the boundary, there's no way to cancel. So that explains why you have this boundary integral. Now, actually, this is also a fundamental theorem of calculus. It says that if you integrate the derivative, you get the function on the boundary. But instead of f of b minus f of a, because the boundary of an interval is just 2 points, right? F of b, f of a. This is now a more complicated situation. The interior is this blob, so you need a double integral, and the boundary is a line, not 2 points, so you need a line integral. F of b minus f of a is a line integral. It's a pretty boring line integral, but hey, we've seen it more or less over here. This interprets f of b minus f of a as a line integral, and in one dimension, everything's conservative, effectively. There's no problem. Every function has an antiderivative. So what we've done is reduced things a little bit, or we've extended things a little bit. Now, as for your question, and your question, someone asked me the question, I guess he's not here, but why was this conservative stuff true? Look at this. If the curl is 0 of the vector field, at least in 2 dimensions we can answer this now. If the curl is 0, then this integral is 0. And this is 0 for any closed loop. And so you see that's the proof, at least in 2 dimensions, that the curl is all you need to check the conservative. Conversely, if this is not 0, then there's got to be some region where this integral is non-zero, and the boundary of that region will not be conservative, in the sense that the integral around the loop will not be 0. So that's where all that conservative stuff comes from. Again, I don't really think the book emphasizes that, but it's nice to understand. All right. Okay, so again, that's the idea. Before I ask for questions, I'll just show you the other version. Okay? So to get the other version, we need to look at an integral now where we take f dot dn. Now n, instead of dr, we want dn. Okay, so what does this mean? dr is that way, dn is this way. Or rather, r is this way, n is this way. So n is perpendicular. Well, dn, whatever. dr, dn. So I'm thinking of n as being the outward normal. N is a unit normal pointing outwards. So here's where I got a little bit trapped last time, and I kind of want to avoid the void by that, just telling you that practically speaking, if dr was dx comma dy, then dn should be equal to dy comma minus dx. Okay, well, we've seen that if you, here's x comma y. If you switch the x and y coordinates but take a negative, then this ought to give you the opposite slope, but over here. So this ought to be normal to it. So this is the point y comma minus x. So that turns out to be the normal. And so for computational purposes, you have m dy minus n dx. And that's the formula that I had great trouble writing last time. And because I don't trust myself, I'm just going to make sure that I'm right. Okay. No problem. So basically then, what is this? What is this integral geometrically? Let's... no, this is still here. We're still going to haven't got the Grun's theorem part yet. So that's to be compared with this. Okay, it has a different physical interpretation. We have our field of marbles or gas or whatever, but at this point, instead of taking the dot product along this way with the flow, we're going to take the dot product normal to the curve. So that's what that measure is. We put a marble right here, and we have these little paths that are, we have these little tracks for the marble to go down that are normal to the curve. And some of the wind is going to blow the thing in the wrong direction, so all I want is the part of the force of the wind that is going in and out. So some of the marbles might move in, some of the marbles might move out. But, so I put a bunch of different marbles. These guys here move in because the force is going there. They can only move in this direction, normal to the curve. The force is blowing this way, so some of it is blowing that way. So if I put a bunch of marbles on the outside and I say, okay, go, and they all can move only in and out, some of them will move in, some of them will move out. And I'm interested in what the net outflow is. Now, if the net flow happened to be 0, and I let the marbles replenish themselves so I have a whole lot of them, then actually the amount of stuff, marbles inside here, will not change. Because the net flow will be positive. Whatever you will be 0. Whatever you lose, you will gain somewhere else. Now, similarly, if it's positive, then eventually we're going to lose stuff from in here. If it's negative, we're going to gain stuff. All right, so this is the net flow outwards. So it's called a flux integral. This integral is called a flux integral. Flux is a fancier word for flow. So it's measuring, the last one is the circulation. It just measures how the marbles move around the boundary. This measures how the marbles move through the boundary. And the form of Green's theorem that's appropriate requires another object. So you remember I announced the curl earlier. Here I've got to announce what's called the divergence in order to make sense of this. And I'll do the three-dimensional divergence. This is the dot product. And this works in any number of dimensions. So in 3 dimensions, this is, so suppose that f is the vector mnp. the divergence says you dot product this del symbol, which we're thinking of as the vector d dx, d dy, d dz. You dot product that with this. So it's dm dx plus dn dy plus dp dz. That's the divergence of a vector field, and it's a scalar. This is a scalar function. Okay, the curl was a vector. The divergence is a scalar. But it's not the same thing as del f or grad f, which doesn't even make sense unless that f is actually a scalar. So I just want to contrast with not that. You're not hitting a scalar function, you're hitting a vector field with this operator. And actually, it's sort of weird. What it means is you just take the x component and differentiate it with x, plus the y component with y, plus the z component with z.
What's the physical interpretation of that?
Well, let's see it in 2 dimensions in a few seconds. So in 2D, the divergence is dm dx plus dn dy. There's no z component. And so given this, here is the version 1 of Green's theorem. And here's what it says. The integral of the normal form, which I will write first as m dy minus n dx, is the double integral over the interior. Again, R is the inside of C. It's the region enclosed by C of dm dx plus dn dy, dx dy. Or more formally, without the components, without the m and n, f dot dn rather, the line integral, is equal to the integral of the divergence of f. And you don't need to muck around with the k component here. It's the divergence of f dA.
So this is version 1.
This is version 1.
Would you put a square on the board right above you?
Where is the square?
Like all the way at the top.
Okay, so that's the definition. Well, okay, f dot dn. The way to compute that in general is using this formula. Just like the way to compute f dot dr is essentially using that formula. Okay, so there's nothing fancy about that. That's a reflection of the fact that dn has this expression. Okay, now here's the deal. This is the Green's theorem in the computationally useful form, just as version 2 is over here. And this is the Green's theorem in the theoretical form, which over here. These are exactly the same thing, because this is the same as this by the top equation up there, and this is the same as this because that's what the div is here. So if you piece together those 4 boxed or circled equations, you'll see that you can see that that equals that. No? Don't believe it? This is the same as this. That's the top equation. This is the same as this. That's the definition of the divergence. All right? Now, what does the divergence mean? Okay? Here's a point. You put a bunch of marbles there that are all close together. And then you let it go. Okay? Some of them move out, some of them... But you put the tracks all leading out. So they can only go in towards the center or out. So depending on which way the wind blows, some of them get pushed towards the center, some of them get pushed out. But there might be more of a flow outwards, or there might be more of a flow inwards. The classical thing is, if you think of this as a gas that's sort of expanding, then everywhere sort of goes outwards in a way. Although if this one's going outwards and this one's going outwards, then there's going to be some cancellation. Well, guess what? That's exactly what this is saying. What I want to do is add the explosive force everywhere. But with the understanding that if something gets ejected out of here, it's going to be into here. So if something gets ejected out of there and something gets ejected out of there, the net effect is 0. So actually, when you add up all these explosive outward forces, all the interior bits cancel out again, and all you're left with is the bits on the boundary give you the explosive force outwards or inwards, which is exactly this flux integral. So it's the same sort of idea. Instead of adding circles and getting the circle around, you add the sort of push out and get the total amount of push out over the boundary. Because the interior pushes against each other just cancel. Pretty neat. Now, when I say they're the same formula, by the way, suppose you take this formula, but you simply call M, let's call M N instead. And we'll call N minus M. So if you replace M by capital N and N, capital N by minus M, then what will happen is you'll get N dy, and then the minuses will cancel out, and you'll get plus M dx. So you
can just flip them like that?
Well, you can't flip them, but let's suppose we take this vector field and find a different vector field where we switch the coordinates and put a minus. Okay? Then this formula will be dn dx minus dm dy, which is exactly this. So what I'm trying to say is, to get from here to here is just an algebraic trick. If you know one, you know the other just by renaming your variables or just changing your vector field. You just, if that's true for every m and n, then for any given m and n, you could just flip these and put a minus in front of one of them, and you would get this formula. So the two versions of the Green's theorem are functions of math symbols. However, when you write them like this, they have different physical interpretations, which are equally valid. All right. That's quite a lot of theory in quite a short amount of time. So, let us do
Sorry, one more question.
quick question, and then I'm going to do examples.
They're the same computation, but they won't necessarily give you the same value.
No, they don't give you the same value. What I'm trying to say is if you know one version of the theorem, then the proof of the other one, you don't need to do a separate proof. You just permute the symbols, and you know, algebraically you can change one into the other. But then the interpretation physically is different. This was question 2 from problem set 10. Okay, so it said let C be the piece of the curve. So C is the piece of curve x squared plus y squared minus 1 equals 0 for y greater than or equal to 0. And it doesn't tell you this, but you ought to assume that it's oriented in a counterclockwise way. So counterclockwise, that's just generally assumed, although it's really remiss of them not to say it. So here goes. The question is to compute, and this is not a closed loop, as we will see when we draw it. So it's just y e to the 2 cosine y plus xy dy minus y squared minus x squared dx. Okay, so what is this loop? Well, it's a circle, radius 1, centered at the origin, but it's only the top part of it. So it's actually just this. All right. So we could try a parameterization if we're actually just going to compute it. The way you would compute it, here's 1, here's minus 1. This is the curve. That's it. The way you would compute it is to let x be cosine t, y be sine t, but you only need t going from 0 to pi. So you could work out dx and you can work out dy, and you could plug everything in here. dx minus sinus t dt, dy is cosine t dt, but look what you'll get. You'll get sine t e to the 2 cosine of sine t. Ugh. It's too nasty to do it. I mean, try it. Write it down. You'll change it into a single variable integral dt. It's not even that hard, and you will see that it is a total and utter disaster. The hope of computing it is basically 0. You can't do it. It's just, the integral is too messy. So the only hope is to use Green's theorem, and you might notice that it's sort of handily formed in the terms of version 1, which we did second. So if we call this M, and we call this N, then we're going to be able to think of this as a Green's theorem in the normal form. We're going to interpret this as f dot dn. So although you don't need to know this to work out the question, we're actually going to be intrinsically working with this vector field, which is just y e to the 2 cosine y. Actually, maybe we do need to know this for the question. I give take back. So this is m comma n. So if you make this identification, then this would equal the integral c of f dot dn. But, okay, do you see how that's true? The integral of...
x squared minus, or minus...
Yeah, it's minus. So look on the right board there. If we can just pan over to the very top right-hand corner of the board. We have f dot dn is m dy minus n dx. Okay? Now, quickly pan back over here, and you see that if I've called this m and this n, this is m dy minus n dx. So this is actually f dot dn. This about Green's theorem. What's important about C, the curve? It's supposed to be, it's a curve, it's simple, but it's closed. It's got to be a loop. In all of these, notice the integrals that I'd written on the right two boards. Don't worry about panning over the right two boards, but I mean, everything we've written had a closed thing. This is not a closed. This is not closed. So, in the words of Family Feud, survey says, wah, wah. Okay, we need to make it into a closed loop. How do we do that? You need to add a piece. You could add the other half of the circle, but there's an even better piece, just along the x-axis. So let's do this. Let's let C1, we'll call it C2, be the C, then C1, where C1 is this, minus 1 to 1, going that way. So C2 is actually this closed curve here. All right, let's see what this gets us. I propose that instead of writing what we did, so this is sort of slightly wrong. Let's now just do the same thing, but take the closed loop y e to the 2 cosine y plus xy dy minus, what is it, y squared minus x squared dx. And we're thinking of this as m dy minus n dx. Well, actually, we don't even need the curl form. If we can remember this form of Green's theorem here, we don't even need, the divergence form. We can just remember this boxed formula and complete the problem just by using this. So don't worry about f. We come back over here. This is the closed loop of C. This is the closed loop C. And according to Green's theorem, version 1, this is equal to the double integral over R of dm dx plus dn dy dx dy. Okay, so that's the Green's computational version of the theorem. It's not the physical. The physical is that the flux integral is the integral of the divergence. But, hey, this is the practical way. So let's see if we can finish it. R, by the way, is the interior here of the semicircle. Okay, so the integral we want, except I called it C, but let me go back and call it C2. I'm sorry. C2 is the whole thing. It needs to be a closed curve. So we already had C, which is this, and then we have C1, which is this. C2 is the whole thing. So, sorry, I forgot to write it a few times, but here it is. Now I'm happy with what I see on the board. All right, dm dx. This is m. This is n. You have to just differentiate this with respect to x. What do you get? Nothing there? Y. How about dn dy? Differentiate that, not with the minus, but just the n. 2y. So you get y plus 2y. Dx dy. Otherwise known as 3y. Well, this is just a double integral. We have to do it, but we've done it before. The 2y is the derivative with respect to y of y squared minus x squared. This is dn dy. You see it? Okay. All right, so how do we do such an integral? Any suggestions? It's a double integral over a semicircle. Any ideas? Polar coordinates. So we're going to use polar coordinates. So we have this double integral of 3y dx dy. Well, in polar coordinates, y is r sine theta, and dx dy is r dr d theta, and r goes from 0 to 1. And what does theta go from? Theta is the angle. It goes from 0 to pi. It's only the semicircle.
But don't you want to go all the way?
No, I'm integrating over this region here.
Ah, we're doing area now?
Yep, we're doing area. That's the beauty of Green's theorem. We've changed a line integral into an area integral. A double integral. Okay, so we have to do this. Let's just quickly do it. You get 3 times the integral. Well, let's just do the damn thing. We have r squared, so this will be r squared, r cubed over 3, evaluated between 0 and 1. So that's 3 times a third. And then we have to integrate sine theta. So that will be minus cosine theta between 0 and pi. So I believe the answer just works out to be 2. Okay, maybe I should check that because I've been making so many damn mistakes. Okay, I'm pretty sure that's right. Oh, I can't even find where I wrote the damn thing down. Seem to be saying damn a lot, but what can you do? Okay, 2. Question. We haven't finished yet. But yeah, but
Say in general, if you don't have a closed loop, the easiest thing is to make just a straight line to the.
yeah, I mean the other half of the circle's not a bad idea. We could easily have computed this integral, but I'll show you why the other side wouldn't have worked in just a second. See, the thing is, we have now shown, so we have seen that the integral we want of this business here, m dy, I'm not going to write out the function again, equals 2. But we don't want this. We want just the top part of it. Okay? So this can be written as the one we want plus this line here. And here I'd better write it out. What was m? Y e to the cosine 2 cosine y plus xy dy minus y squared minus x squared dx. We've seen that equals 2.
What equals 2 when you add them together?
This is what we want. This is this part plus this part. Okay, when you do this integral here plus this integral here, you get the integral around the whole thing, which is the same as the integral of the divergence inside, which turned out to be 2.
Isn't the right part also includes the half of the circle?
No.
It is the function though.
You have this plus this. That's the curve. That's the C2. Okay, now if you used the bottom half, you would have a nasty integral left, just like we started with a nasty integral. But we will see that when we do this, we can actually work out this line integral directly. In fact, it's not bad at all. A parameterization along C1 After all, c1 just goes from -1 to 1. So let t be equal to x, and then y equals 0, because it's just along the x-axis. So dx is dt. You don't even need a parameterization. You can more or less just ignore y. But anyway, let's play pat and look at this integral here equals the integral from -1 to 1, because we're going that way. Y is 0. Xy is 0 times t. dy in any case is 0. Minus y is 0. X is t. dx is dt. Because x equals t. So this integral here is just the integral from -1 to 1 of t squared dt, which works out to be 2/3 if you do it. So actually, had the problem been, instead of integrating this nasty thing along the semicircle, to integrate it along the line, it would have been very, very easy, 2/3. But it wasn't. So what do? We found the whole integral along, and then all we have to do is subtract the integral along the line. So the integral we want, which is this, y e to the blah, 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 the integral we want equals 2 minus 2/3, which is 4/3. And that's the answer. Tricky stuff. Tricky stuff. Okay? Let's just review the idea again. We want the integral here. We find the integral here. We find it by doing a double integral inside there, using Green's theorem. We get an answer, which was 2. And then we say, okay, we found this. But we just want this. This plus this equals this. This was 2. That was easy to compute as 2/3. Therefore, this was 4/3. That's the way to do it.
You just integrated the function dx. You called it dt, but it's just like integrating the whole thing dx.
Yeah, I mean, you didn't have to call xt because, right? I mean, the fact is y was 0, in fact, y is 0. If you're just going along the x-axis, it's a very simple parameterization. You still need to know how to compute line integrals,
Okay,
right?
when you integrate this thing dx, I see 2 minus, I see 2x, not x squared.
X squared, t squared dt.
Okay.
All right? I tell you, these things are a lot trickier than what you've seen before. But that's the way. That's how it is. This last part of the course is hard. Sorry? The book's explanation is lacking? Well, that's why I'm here, partly. All right, here's another question. This is a nice one. This comes from a quiz in spring '04. Let C1 be the curve x squared plus y squared equals 1. And let C2 be the ellipse x to the x squared over 4 plus y squared over 9 equals 1. All right, and it says here is a vector field, f, which is x over x squared plus y squared, comma, y over x squared plus y squared. 2 dimensions. Okay, and it says, note that f is not defined at the origin. Because x plus 0. Okay, so that could be a problem. Now, here's the deal. Calculate, so part A says calculate the outward flux of f. So find outward flux of the vector field f across C1. Okay, we'll do that first. We need to understand that a flux integral is actually a normal integral. Okay, that's the it's really good to know that formula, m dy minus n dx, where this is m and this is n. All right, so let's just substitute that in. X over x squared plus y squared dy minus y over x squared plus y squared dx. Now, C1 is the circle x squared plus y squared equals 1. And we can compute this directly by taking a parameterization. In fact, the correct parameter, well, the best parameterization is x equals cosine theta, or t, y is sine t. So here's a good example. This is similar to a line integral that we just did, except that we're going around a circle. So this is a nice computation without using Green's theorem. This is just, we're going to compute this line integral. And it's not very hard. Dx is minus sine t dt. Dy is cosine t dt. And we just plug everything in. Oh, by the way, notice that x squared plus y squared is 1. So actually, this integral is not so bad. So x is cosine t. The denominator is 1. Dy is cosine t dt. Minus y is sine t. The denominator is 1. And dx is minus sine t dt.
The reason why you thought of doing it like this is just so that integrating is going to be too long. I mean, why not just integrate it like that?
You can't integrate this like this. You cannot treat this line integral around a circle as a one-dimensional integral. Just don't forget that you know how to integrate these in the normal sense. It just doesn't work. Okay? These are different integrals. This is not just a to b. You've got this dy stuff, you've got this dx stuff. This is actually a differential form, not a regular thing. And if you just try to integrate it, I don't know what you're going to use as the bound, for example. So forget, for a line integral, forget it. You have to do a parameterization. Or you have to do Green's theorem to convert it into a double integral. That's the only way that you know of computing a line integral. Parameterization or clever stuff with Green's theorem. Okay? You can write that down if you want. All right. Anyway, this is particularly nice. The parameter goes from 0 to 2 pi. See, we've gotten rid of x and y. We've related them in the circle by the parameter. And now this is a one-dimensional thing with dt. And it turns out to be cosine squared plus sine squared. So it's a piece of cake. It's just 1 dt. So it's just 2 pi. It's just 2 pi. All right? So, now, the question is, could you have done this with Green's theorem? In order to do this with Green's theorem, you would have to integrate over here. But there's a problem. The vector field is not defined at the origin. That actually kills off the idea of using Green's theorem. And I will show you why. Part B said this. What is the divergence of f? What is the divergence of f? Compute that. Well, according to this, it's dm dx plus dn dy. That's the formula. M is this thing up the top of the board, x over x squared plus y squared. What a pain. Well, we have to work it out. We have to differentiate x over x squared plus y squared. And then we have to differentiate y over x squared plus y squared. So you use the quotient rule here. You get x squared plus y squared times the derivative of x, which is 1, minus x times the derivative of x squared plus y squared, which is 2x, all over x squared plus y squared, all squared. And then you do the same thing for y, but the beauty of the y is that you just use the same, you don't have to redo it because everything is symmetric. You'll get exactly the same thing, but instead here you'll get minus y times 2y. Switch x and y around. Anyway, that works out to be 0. You have x squared plus x squared minus 2x squared, and you have y squared plus y squared minus 2y squared. and somehow everything cancels and you get 0. Okay? So that's, if you don't believe that computation, it's just differentiation. Partial derivatives way back to the beginning of the course, so just check that out. Now, the third part, but actually even before I do the third part, I just want you to observe something. We have computed this. The first part we computed that f dot dn was 2 pi, and we did it directly. In the second part, we computed the double integral, actually we computed the divergence of f everywhere equals 0. So imagine we use Green's theorem in the version 1 with the normal. I'll put a big question mark there. The interior of the circle is R. That's version 1 of Green's theorem. So according to this, the divergence is actually 0. So this is the integral of 0, which should be 0. Now that is not what we found. When we computed it, we got 2 pi. So if you compute the line integral, you get 2 pi. If you instead take the divergence and find the area, you get 0. Now, Green's theorem says they're supposed to be the same thing. What goes wrong? What goes wrong is that for Green's theorem to work, the vector field f needs to be defined everywhere, and even one point is big enough to screw it up. In effect, you have infinite you have divergence everywhere of 0, and yet you have some flow out of here of 2 pi. What's going on is that there's actually an infinite divergence there. But since it's at one little point, somehow that's enough to have a flow. There's like an explosion out of there. It's like a black hole, a singularity there, and nothing else anywhere. And somehow the amount that comes out, even though it's 1 point, is 2 pi. Weird. Anyway, so that's a cautionary tale. You can only use Green's theorem if the function is defined everywhere. Anyway, the third part of the question, this is germane to the third part, which says, now C2 was this ellipse, which I had written on the other board, goes from 2 to, well, it's this. There's the ellipse. This is C2. Whereas C1 was in here. C2 is there. So, now we're supposed to compute this. C2 f dot dn. Well, we could try to do the integral again, but actually it's a waste of time. So in order to do this, I need a slightly different version of Green's theorem. So it turns out that Green's theorem is not just true for a single curve in its interior, so we need a different version of Green's theorem. Either version, V1 or V2 of Green, we're allowed to have a region that looks like this. Actually. And a vector field defined in the boundary here, but not even necessarily in between. So if C is C1 and C2, then either version of Green's theorem, for example, the divergence version, f dot dn over C, this is still true. Okay, this integral means you integrate here, and then you integrate the other way, this way. So it's a different version, but it still makes sense. We're trying to measure the net flow out of this region here. So how do you see what flows out? You look at what flows out of C1, but you subtract what flows into C2. So you need an inward thing. Now if you start adding up all the explosions out of all these places here, you will find that you get the explosions out this way and the explosions out this way, or in this way. So the explosions out this way is the normal integral f dn, but to get the explosions in, you have to either reverse the normal, or if you actually don't reverse the normal, you have to reverse the direction around the curve. So you keep.
Flux over this region.
So this is the flux over this annular region. So it's a different version of Green's theorem. But the interpretation of this is you have to interpret this as the C1 going this way, f dot dn, minus, or I don't know whether to write it, plus C1 going the other way, C2 going the other way.
Or minus the same.
Or you can replace this term with minus C2 going the normal, as in the counterclockwise way. So you can either go this minus this, this minus this, or you can go this plus this. It's best to keep the normals the same, always going outwards, because otherwise you see, the other thing is you could do it this way both times with a plus, as long as here the n goes that way and there the n goes that way, but that's just dumb. N always means outward normal.
You want to add what's coming, you want to subtract what's going into C2 or what's going out?
You want to, so let's be careful about the add and subtract. To see what the net effect of outwards is, you need to see what's going out of C1 minus what is going out of C2. I.e., what's going out of the region is what's going out of C1 and into C2. Yeah, so if you subtract what's going into C2, this is the same as adding what's going out of C2. Exactly. Yeah, I mean, you can get yourself really tied in knots. So I just like to think of them as going in opposite directions. Okay, so anyway, the point is that in this example, we're nearly done. Actually, there's no more computation to be done at all, which is nice. So here goes. What we do is we have seen that the integral around here is 2 pi. Now we're trying to integrate around here. This inner integral, line integral, turned out to be 2 pi. So here goes. The integral around C2, going clockwise, of f dot dn. Let's do minus the integral of C1 f dot dn, going the same way, counterclockwise, is equal to, by Stokes' theorem, the divergence. So this is Stokes' theorem applied to this annular region. F is really bad in the middle, it doesn't matter. As long as f is good in the shaded region, we're okay. Now, this we knew, this is what we want. This is 2 pi. And we computed that the divergence is 0. So blissfully, we do not have to do a double integral.
When did you compute the divergence was 0?
Over this board.
That was part B.
Yeah, that was part B.
I thought our computation of the divergence was flawed because...
No, the computation of the divergence was fine. It's just that the divergence doesn't exist at 0. Nothing wrong with the divergence computation. It's fine everywhere except at the origin. Divergence exists everywhere but the origin.
Okay.
What's flawed is if you try to use Green's theorem with just over the whole circle, not forgetting that you have a discontinuity there. It's like using the mean value theorem or the intermediate value theorem with a discontinuity. It doesn't work. All right? So the point is that this also equals, without even having to compute it, it equals 2 pi. Same as the first integral. Actually, there's nothing special about the ellipse at all. If you have any curve that goes around the origin once, it'll be an integral, it'll have an integral of 2 pi. Any curve. So it's almost conservative. It's almost a conservative situation, in a sense. It's a modified version of conservative, but it's a little trickier because you have a point that you have to while around.
Any curve around the origin?
Yeah, if you find this integral, it's C2, yeah. I mean, there was nothing special about the ellipse. We didn't use it at all.
Has it, what is that, the flow?
Yeah, the flux. The flux through it will be 2 pi. For this vector field.
It doesn't, for this vector.
For this very specific vector field.
Okay.
By the way, can you tell me what the integral would be if you don't go around the origin, like that? What's that integral? The line integral is 0. Because then you take back here. And you can use the straightforward form of Green's theorem. And the integral along here will be the double integral of the divergence inside. The divergence is 0.
That's Stokes.
Green's theorem. We're all Green's theorem.
Okay.
Did I say Stokes? I meant Green's.
So this isn't Stokes, what you just did here?
Green's. Stokes' theorem becomes Green's theorem in 2 dimensions, so it's all part of Stokes, but I meant Green's. I haven't done Stokes yet. I doubt that I will in half an hour, but what can you do? This stuff is good, right? Anyway, if you integrate over any loop, this particular vector field f with no divergence, the flux integral is 0 unless it goes around the origin, in which case it's 2 pi. What if it goes around the origin twice? It'll be 4 pi. What if it goes backwards? It'll be 2 pi. Minus 2 pi, rather. It'll be minus 2 pi. So actually, it's really easy to work out the integral of any curve. You just have to work out how many times it goes around the origin net. It's called the winding number. And then multiply by 2 pi.
If it doesn't go around the origin, it's 0.
It's 0.
Because
The divergence inside is 0.
or close to.
Well, the divergence everywhere inside here is 0.
This is all just
See, for this vector field, in fact, any vector field with 0 divergence except at the origin.
So we proved that it was 0 before?
No, we haven't proved it, but we can prove it. We just use Green's theorem here. Here's a closed loop that doesn't go around the origin. Okay? The integral of f dot dn, the flux integral around that closed loop, is the integral of the divergence inside that region. And the divergence is 0 everywhere except at the origin, where it's not defined.
The divergence is 0 everywhere. Wow.
We computed it. There it is. We worked it out.
Okay.
It doesn't work at the origin because the function isn't defined. So this argument does not work for a curve that goes around the origin, because this has to exist everywhere inside R. It does not exist for this curve. So we computed using a specific curve of the circle that it was 2 pi for this specific example. That is very much like the previous example where we couldn't do this integral, we could do that integral. Actually, if you try to do the ellipse thing directly using a parameterization, you'll find it's terrible. It's a real mess. A mess of trigonometry. So, but the beauty is you just have to do it for the circle, and then you have it for every curve. It's pretty amazing. I mean, you wouldn't believe it, but that's what it is. Question?
I think I was just getting confused because I thought that the divergence was bounded by the region, but it's the divergence.
The divergence is a function at any point which tells you how much of a spread there is, right? And the fact is, this function has spread 0 everywhere except here where it sort of doesn't make sense. And here, the spread, there's no pressure from anywhere inside. That's the point. The gas is neither expanding nor contracting. It's just kind of net 0 everywhere. And so when you get to the boundary, there's no pressure inwards or outwards. So this integral is 0 in net. Question?
So if it didn't go through the origin and the divergence then wasn't 0, would it be the same thing and you'd actually just have a number? Yeah, and so it wouldn't always be the same.
So you're saying, okay, I think, just rephrasing your question, I think, how's this for a rephrasing and an answer? If the divergence wasn't 0, and you still took the same curve, then you'd have to do this integral. But you would get an answer. Okay? And then that would tell you how much more than 2 pi. But then you would need to, it would depend on the curve, because you would need to do a double integral over the specific region between the circle and the ellipse. Here, it doesn't matter what the region is. By the way, I should say for a few seconds why this weird version of Green's theorem actually follows from the original version. Okay, so what you can do is, you've got a problem in the middle, say, so you have this loop here, you have this situation. What you can do is actually you can reduce it to the other situation almost by doing this. Now this region is simply connected, right? It's a blob, it has no holes in it. You can't go around this hole because you can't go through there. And then this integral is fine. The divergence makes sense everywhere, even if it doesn't inside here. And then you just have to look at what the curve is. So you go once around here, and then you go here, and then you go backwards around here, and then you go here. And actually, when you add up the line integral, you almost get the whole thing of the outside, except for that little bit. You almost get the opposite direction on the inside, except for that little bit. And then this is almost cancelled by this. And now all you need to do is let these things go squish, squish, squish until they're basically in the limit the same. This bit cancels this bit, and you just get that way and that way. So the proof of this form of Green's theorem actually is done in a very sneaky way by slitting through the other one. So that's another approach of looking at it. Or you can do the physical version that I did with the flows in and out. I kind of like the sneaky one because I'm more of a mathematician than the physicist. All right. So that's all I have time for in terms of Green's theorem. And clearly you need to do a whole lot of examples. So I'm hoping over the break you can do that, and then we'll come back, we'll review all this stuff, and then we'll do a whole lot more examples, because there are plenty of them in the previous finals and quizzes. There's no shortage of them. You have to do them all, by the way. You don't have to, but you should. You should. Okay, so you have this break coming up in a couple of weeks, and you should really do every question. That's my advice. Try to do some of them under exam conditions as well. Anyway, let me say, I'm going to give myself nearly half an hour more because I said I was going to go over time. I need to tell you about surface integrals. I don't know about surface integrals and maybe even Stokes' theorem, but I won't have much time for that. All right. Surface integrals. Okay, we've done line integrals. Surface integrals look like this. You have some surface in 3 dimensions, and what you have is a function, scalar function f, that's defined at every point on here. You want to add up the values of f on here. Well, it's like a line integral, except that it's on a surface, which means that you kind of have to carve up the surface into little chunks, which are actually going to look like little parallelograms. Almost. I mean, they're curvy, but they become closer and closer to parallelograms. And you're going to say, okay, take the value of the function on this chunk times the area, and add that up, and then let the chunks go to 0. And so you end up with an integral which looks like this, f d sigma, to be compared with f ds for the line integral. And this is over a surface S. It's a double integral. Why a double integral? Even though it's in 3-dimensional space, the surface is 2 dimensions. At every point on the surface is sort of that way and that way. The 3rd dimension, which is the cross product of those 2 vectors, is actually off the surface. It's the normal to the surface. So on Earth, 2 dimensions. Outward normal, up and down. Okay? So, again, this has an interpretation as a sum. What we are going to want to do is compute the thing. We need to be able to compute a surface integral. And one nice application is that if f is just 1, this will be the surface area. Because you're just adding up all the little d sigmas, which just gives you the area. But if you have an f there, then you're sort of counting some of the area in a different way. So if f is 3 here, you're sort of counting that 3 times as much, 3 times d sigma. If this is minus 1 over here, then you're taking minus that area. So that's sort of like a weighted sum. That's the same as line integrals. As well, the integral of ds for a line integral is the length. The double integral dA is the area, etc. The volume. So the integrand is 1, you just get the mass of the thing. All right, so that's what we're trying to do. there are two ways of computing this. And I really would have loved to have time to explain this. Maybe if anyone wants to stay afterwards, I could give a brief explanation. But I won't really have time to do it on the video because I need to do some examples. So let's just say there are two ways of computing this. And in both cases, we need to know what d sigma is. So case 1, or method 1 for computing. Okay, there's two methods. Method 1 goes like this. The surface looks like f of x, y, z equals constant. But I kind of want to only consider a surface which has a nice projection onto the xy plane. So I'm thinking of z as a function of x and y. So it looks like this. Okay, so there's the surface. What I want to do is consider the case where it doesn't wrap around. As in, there's only one shadow. So the shadow would be some area R. This is the shadow. And this is in the xy plane. But this is the z. So it's no good if there's a multiple shadow. This method doesn't work. You'd have to break it up into two surfaces. So this is the surface, and this is the shadow. So once you've set it up like this, there is a formula for d sigma. And here it is. You take the gradient of f, and you take its length. So this is length of the vector. And you divide by, you take its dot product with the k vector, which of course is 0, 0, 1. And this, because the dot product is a scalar, this is actually just a regular old absolute value. The book doesn't make that very clear.
Why is that? Obviously 0, 0, 1.
K is 0, 0, 1. That's what it is. Right? I is 1, 1, 0, 0, etc. Okay, so what I'm saying here is that wherever you see d sigma, you can replace it by this. Now again, this is a vector. So this is the length of the vector. But when you dot it with k, that means just take the z component. So in other words, this is just the z component of that, i.e. just df dz. And we're taking its absolute value. So it's sort of confusing that that's a length and that's an absolute value, but there it is. So if you know that formula, you can actually compute anything. So that's the entire content of 16.5 in a way, although you have one other thing, and I wonder if I need to do that first. Let's see the example that I wanted to do. Nope, don't need to do it first. For the second part, actually I don't even need to do it for the second part either. Okay, so here is an example from 2003, final. So this is a real final. Let S be the part of 2x squared plus 2y squared minus z squared equals 0, lying inside, or within, well, inside x squared plus y squared minus 2x equals 0, and also z is greater than or equals 0. So the question is, find the area of S. All right? So what is this? It's always good to sketch this. This is a cone. If this was a 1 or a minus 1 or some other number other than 0, you'd have a hyperboloid. But this is a cone. And it looks like this. Z squared is 2y squared, so it's actually got a slope of root 2. So here's x, here's z. better draw in a y-axis. Okay, so that's the whole cone. Now we only need z equals 0, z greater than 0 rather. So actually we don't really need this bottom part. However, we only need the part lying inside this. Now what is this? This says x squared plus y squared minus 2x equals 0. That's the same if you complete the square. You'll find it's x minus 1 all squared plus y squared equals 1. So that is a circle in the xy plane like this. Center 1, 0. And so actually it's a cylinder in the xyz plane. So you've got some bizarre bit of a cone that only goes up to here, but trapped inside a cylinder. So it's just a finite bit of surface. And then the question is, what's its area? Sort of hard to envisage.
Once you know this physical interpretation, is it any easier just to calculate the surface area of the full cone and halve it?
Well, it's not really half, though. See, it's sort of hard to draw. But somehow, when you carve this circle, you won't get the whole thing. It's not just half. It's very difficult to draw. But
okay, I see why it's not half.
Yeah, it's some sort of weird shaving. It's like a. You still get the bottom part, but the cross section around the side will not just be like that. It'll be some sort of wedgy thing. I haven't even worked out what the surface of intersection is. May not be a bad idea. But in the interest of saving some time, let us actually maybe it'll work out to be half. It won't, but you know we'll see what it works out to be. Okay, so the beauty of this thing is if you know any point in the xy plane, you know what z is, right? I'll give you xy. And z squared is this, but z is greater than 0. We're ignoring the bottom half of the cone. So actually we know that z is root 2x squared plus 2y squared. Yeah? Not the minus, just the plus. So actually the only parts we have to worry about is the part where x and y lie in here, because we're just taking a cylinder. So they lie in a circle. So actually the problem more or less gives you the shadow. Not of the whole cone, but of the part of the cone that you want. So the shadow region equals the circle x.
How do we know that all the circle is actually shaded by the
cone? Because okay, so the question is why? How do you know that the whole circle is shaded by the cone? And the answer, I repeat it for the video. So the answer is that every point is shaded by the cone. That's what I was saying by here. So give me x and y, and there's one unique point. If I go up, I'll hit the cone.
Right.
So I only care about the point of the part of the cone in that cylinder. So every point in there will hit some point in the curve.
Why is it a circle and not a semicircle?
Well, they just said x squared plus y squared minus 2x equals 0. They didn't say x had to be positive. This is the equation of a circle.
Yeah, no, I think the flat side, wouldn't the flat side be against the y-axis? If you just bring down the,
Well, let's see if we can work it out. Since you,
if you look straight down,
if you look straight down, straight up, then here's the circle. So imagine the cone going in like that. So you're getting this part of it. I don't know. Can you imagine like the cone going whoosh, and then just cut out that little bit? So it's a pretty weird shaped surface. It's not half the cone.
yeah.
Okay. Anyway, luckily you don't need to visualize it to finish the question, or else we'd go mad. I don't know. The best thing I can say is take an ice cream cone. Don't put ice cream in it, and then take another circle, put it through the point, and try to cut it, and you'll see you don't get half the cone. Anyway, let's finish the question. So according to this, we have to work out what d sigma is in the xy coordinates. Well, to find d sigma, we use this formula. Yeah, I'm certainly not going to have time for Stokes' theorem, I'm afraid, but what can you do? I'll continue in January. Okay, so del f, or grad f, absolute value, or length of, so we need to work this out. So what is f? Well, let f of x, y, z be this function which describes the surface. So we need a level set of level 0. We compute...
Why 0?
Well, because it's 0 here.
Okay.
But this part would also work if you had 1 or minus 1.
Okay.
The thing you'd have to be careful of is having 2 shadows, 2 points, but we're okay because z is greater than or equal to 0. So you have grad f is x derivative is 4x, the y derivative is 4y, and the z derivative is minus 2z. The length, and you need to take the length of this, which is root 16x squared plus 16y squared minus 4z squared. That's just the length, plus 4z squared, sorry. That's the length formula. You square this and the minus goes away. Now, on the other hand, the z component of this, you just pick out the z coordinate, which is minus 2z. And this is a regular old absolute value. And because z is positive in this example, we get rid of the minus sign. So, the question is, what is d sigma? Well, d sigma is the ratios of these two things. 16x squared plus 16y squared plus 4z squared over 2z. Okay, so what are we trying to find? We're trying to find the surface area, which is just the double integral over our surface S, which was a weird part of an ice cream cone, d sigma. So according to this, it is the double integral over R, the shadow region, of this quantity here. I should have said this is dx dy. Actually, I left out this formula there out of sheer tiredness. May I insert over here a dx dy? Okay, that changes the d sigma into dx dy, where x and y move over the shadow region. This now clarifies that point. It didn't really make much sense without it. Yeah. Okay, so we've reduced this rather opaque looking thing to a function, something we can actually compute. There's one problem. Z is a function of x and y. And we need to get rid of it first before we do this. So we need to somehow get rid of z, where z, well, what do we know? We know z squared is 2x squared plus 2y squared. But it's a bit of a mess. So in order to make this really clever, I'm going to pull the 2z into the square root, where it becomes 4z squared. So I pulled it into the square root. 2z all squared is 4z squared. And now I can simplify a little bit. I get 4x squared plus 4y squared over z squared plus 1. Okay, so somehow we still have to eliminate the z squared, but you notice there's a certain nice symbol, there's something nice about here. I mean, z is never 0, so if I do this, I get 1 is 2x squared plus 2y squared over z squared. And actually, that's like half of what we have here. So this So, yeah, it is pretty tricky.
To solve it?
I expect you to solve it. 2. So it's root 3 outside of the double integral over r. What is r? It happens to be the circle of radius 1. So let's not bother using polar coordinates. We know the area of a circle with radius 1. This is the area of the shadow, i.e. circle radius 1. So that's root 3 times pi. Pi r squared. Radius is 1. So that's it. So you've reduced a surface integral to the integral in the xy plane. That's exactly what this method does. We've started off with a surface integral over space, but what we've done is by working out, essentially what we've done is we've projected it onto the shadow, which happened to be a circle, by saying, well, over this area, how much is the area of the surface bit? And for the cone, because the cone is such a nice shape, actually what we've shown is that for every little bit of area here, this bit of area on the slope part of the cone is root 3 times as much. No matter where you are, it's root 3 times as much. Pretty nice. But the cone is not very interesting. Other surfaces, it won't be root 3 everywhere. It'll be a different number depending on how the slope of the surface is. But the point is, if you know what the ratio of this is to this is, and you add up all of those times that ratio, you will get the surface area. That's how much more area you have suspended above than just below. Pretty nifty stuff. Okay, here's another example of a surface area, except that it's not a surface area, it's a surface integral. So here goes. And this will probably be it. This is going to have to be it. Okay, it says z is the part of the surface, S is the part of the surface z equals x squared plus y squared, with z less than or equal to y, and x greater than or equal to 0. And then it says find the integral of xy over z d sigma. Over there. Well, let's try to draw it. This is no longer a cone. It's not z squared. It's actually a paraboloid. So it looks like this. Let's do this. X, y, z. So it's a paraboloid. Okay, but we only need x greater than 0, so we'll chop off the left half. And actually, we only need the part where z is less than or equal to y. So somehow we have to take a plane that's like at 45 degrees going up, and we have to chop off a whole bunch of this. So it's actually only going to be a little bit of the surface. I don't know. Again, it's bloody hard to draw. And you're supposed to find this. All right. Well, how are we going to find the shadow region? How are we going to find the shadow region? We need the points x and y. So we need to find all the x's and y's. So for the shadow first, we need to find the points x, y satisfying x greater than or equal to 0 and y less than or equal to z. Y greater than or equal to z. But z is x squared plus y squared. So we need to find all the points where x is greater than or equal to 0 and y is greater than or equal to x squared plus y squared. Well, this is very simple. What it's for. This says that x squared plus y squared minus y is less than or equal to 0, i.e. x squared, and we complete the square. You need to add a quarter to both sides, and you'll find that it looks like this. So the shadow region, after just the algebra, I mean, it's completely impossible to see from the picture that I drew, at least. Maybe you're a better artist than me. But the algebra tells me that I need the circle, center a half, radius a half, center 0, half, radius a half. And this is the shadow. And again, exactly. But also we need x greater than or equal to 0. So it's not the whole circle, it's just the semicircle. Thank you for that. I should have said it in one go instead of. So you get just this right half of the circle. So that's the shadow thing. And again, for every point in this shadow, you can find out what z is. Z is just x squared plus y squared. So another way of drawing the damn thing is to draw the shadow region first, now that we know what it is. And just draw the paraboloid above it.
You didn't draw it right, you did?
What, this?
It's above that.
There's x, there's y. Oh yeah, you're right, I didn't draw it right. Thank you. I was being optimistic. So it actually is sort of highest around here in the middle somewhere. I don't know. The whole thing's just a mess. I have no idea what it looks like. Okay. Anyway, but I still propose to work out the problem, and I propose to do it in the next 4 minutes. All right. So now what I need to do is repeat the same sort of computation, and it goes like this. I let f of x, y, z be x squared plus y squared minus z. Or did I want to do it the other way around? It probably doesn't make a difference. Actually, it doesn't make a difference. But I might as well be consistent with the solution that I once wrote down. All right, I did do it this way. Now, why do I do this? Because that equals 0 for the surface. Right? I just took the original equation up there, z equals x squared plus y squared, and I threw everything on one side. All right, so grad f is 2x, 2y, minus 1. So the length of it is root 4x squared plus 4y squared plus 1. Just square all those components, add them up. Grad f dot k is just the z component, which is 1, is minus 1. So its absolute value is 1. So d sigma, which by the formula that we've learnt is the length of grad f over the absolute value of the z component, is equal to just, with a dx dy, man, I always forget that, is root 4x squared plus 4y squared plus 1 dx dy. The denominator is 1. All right, so we're in good shape. So let's finish this off. Still requires a little more work, I'm afraid. Now we don't just have a surface area, we actually have an integral with an integrand. So we want this integral, x, y, over z, d sigma over s. So we're going to have x, y, over z over the base region R, which is the semicircle. And then the d sigma is going to be root 4x squared plus 4y squared plus 1 dx dy. Now we again have to eliminate z, and nevertheless that's not hard because z equals x squared plus y squared. Anyway, I have successfully reduced the situation to a plain old double integral where the region is this. But it's still not quite a trivial thing. With all these x squareds and y squareds, suggestion is to use polar coordinates. So in polar coordinates, x is r cosine theta, y is r sine theta, x squared plus y squared is r squared. This will be root 4r squared because of the x squared plus y squared plus 1. And the dx dy is r dr d theta. But we have to be clever about how we compute the angle and the theta. So, well, the angle and the r. So if here is r and here is theta, we do our old trick here. That's a right angle. That's pi over 2 minus theta, so this is theta. And if I compute sine theta, this diameter here is 1. So sine theta is equal to r over 1. So actually, given any value of theta, you start at r equals 0 and you go up to sine theta. And which thetas do we need? 0 up to pi over 2. We only need half that. Ugh, what a pain. Let's work out what we've got here. We've got 0 to pi over 2, 0 to sine theta. How many r's have we got? These cancel out. And you just have r root 4r squared plus 1. And then you're going to have left over a cosine theta, sine theta, d theta. But we'll do the dr part first. And so this integral is not so bad. 4r squared plus 1 to the power of half. Well, if I did 3 halves and differentiate, I get 3 halves times 8r times 4r squared plus 1 to the power 1 half. So that's the factor that I need to move over to the other side. So just a single variable integral, you will have 1/12 4r squared plus 1 to the power 3 halves. See where the 12th comes from? This is basically 12. It is 12. So, yeah, you can do a substitution, get the same thing. Evaluated between 0 and sine theta times cosine theta, sine theta, d theta. Take out the 12th, do the substitution, and you will get 2 terms. You'll get 4r squared, 4 sine squared theta plus 1 to the 3 halves, and then the other term is actually minus 1. Anyway, it's a single variable integral now, and we're already way over time. It's not as bad as it looks. You split it into 2 pieces, and in the first one, the cosine theta is the derivative of the sine, and actually it is in the second one as well. So I don't see any reason why you can't just complete that integral, and I believe, although I have had no way of checking it, because I didn't use a computer, I think you get the amazingly disgusting expression 1 over 2 over 45 to the halves minus 1 minus 1/48, which could be maybe simplified further. Anyway, so look, I showed you one method of the d sigmas. Unfortunately, there's another method which I don't have time for. Fortunately, there's another method. Unfortunately, I don't have time, using parameters, which is covered in 15.6. Then you do a version of Green's theorem in space called Stokes' theorem. And then you do another version called the divergence theorem that is really, really cool. But I don't have time to do it. So unfortunately, I'm going to be out of the country next week, where I would have liked to have finished this. But instead, search your email and you will see that in January there will be plenty of review sessions.